All right, switching gears, for page 6 of the final exam review packet, we're going to review energy diagrams. I'm going to draw the only two possible shapes of an energy diagram. There's one that goes up and way down, and there's one that goes up and stays up. So the purpose of these diagrams is to show what's going on energy-wise during a chemical reaction. So let's say, for example, we've got methane gas plus oxygen gas, and we're making carbon dioxide plus water, combustion reaction. I'm going to just write the mirror image, the reverse reaction up here. There are some values that are important. There's a certain amount of energy that's required in order to get the whole reaction going. That's called the energy of activation. And during this part, bonds are being broken. I don't know why I drew an M there. Bonds are broken. So in my little example here, the carbon is bonded to 4 hydrogens. Those bonds are broken. And the oxygen double bonded to another oxygen, broken. And then new bonds form here. Notice that in this reaction, you get more energy from new bonds forming than you had to put in. Overall, that's a negative heat of reaction. This is the shape of all exothermic reactions, where energy is released. Okay, then we've got the opposite. This side we've got an endothermic reaction. Overall, energy is absorbed. So check this out. This is the energy of activation for the reverse reaction. It's a lot bigger. Okay, and that makes sense because it'd be pretty hard to get carbon dioxide and water to turn back into methane and oxygen. And the heat of reaction would be positive. And it's the same here. Bonds are being broken up here, and new bonds are being formed here. Okay, let's apply this to some of the examples. 47. Draw the energy diagram for the reaction below. Be sure to label everything. So I notice right away that the heat of reaction is negative. So that means I'm going to draw my exothermic shape. I'm going to put my reactants here and my products down here. It says the energy of activation is plus 375 kilojoules per mole. And my heat of reaction, the difference between the reactants and the products, is negative 165. So how much energy did it take to break the bonds? Remember, this is the part where bonds are being broken. So it took 375 kilojoules per mole. What's the total energy released from making the products? So we've got to add 375 plus 165. That comes out to be 522 kilojoules per mole. Would a reaction with an activation energy of 157 be more or less likely to occur? Well, that's less energy than it takes this one to occur. So it would be more likely to occur because it requires less energy to break the bonds. Then there's a second question here. Is the reaction above exo or endothermic? It is exothermic. More energy is released from making new bonds than it took breaking the bonds. Then there's a question about drawing the reverse reaction. So in the reverse direction, if you added those two up already, you've already got this part. It would take 522 kilojoules per mole, and I can write out those products, or what were once the products, now as the reactants. And this time we're making the 2H2O2, and the heat of reaction would be positive 165 kilojoules per mole. The heat of reaction is just the opposite in the reverse direction. All right, moving on to one of these where we calculate how much energy it takes to break the bonds, figure out how much energy we're getting back, and then calculate the heat of reaction ourselves. So first it says write out the balanced reaction for C3H7OH. If it's combustion, you know that it's plus O2 and that it always makes CO2 and H2O. To balance this, we need to use the Cho method. So C3, 3C. There's 8 H's, so 4 times 2 is 8. There's 6 oxygens here, plus another 4, that makes 10, but there's 1 here, so we need 9 here. So we got to put a 4.5. We cannot leave it like that, so let's multiply all the coefficients by 2. So 2, 9, 6, and 8. What's the total energy required to break all the bonds in the reactants? Well, it's helpful to have the reactants drawn. So I'm going to draw out 3 C's, draw my H's as I go. There's 7 H's there, and then my OH. And then my other reactant is O double bonded to an O. So I also have to pay attention to my coefficients because there's 2 of these molecules that we have to break everything. So first let's look at C-C bonds. There's 2 CC bonds per molecule, and there's a 2 out in front, so that's times 2. And then I check my chart up here. It takes 83 calories per mole. Okay, so we can calculate that out. It comes out to be 332. Okay, then let's look at our CHs. 1, 2, 3, 4, 5, 6, 7 CHs that need to be broken. Times, there's 7 in each of those 2 molecules, times 99 is how much it takes up here, it says. That's 1386. There's just 1 CO bond times 2 molecules times 86. That comes out to be 172, plus there's 1 OH. So 1 times the 2 molecules times 112. We've got 224. So if I add all of this up, so far, we've got 2,114 calories per mole required. But we can't forget the oxygen. We've got 9 of these O double bonded to an O's to break. So 9 times 118 is 1,062. Plus that 2114. So if we add all of that together, it takes 3,176 calories per mole to break all the bonds of the reactants. Now let's think about all the energy we're going to get back when we form these new molecules. We are forming 6 carbon dioxide molecules. Each one has 2 C double bonded to an O's in it. So we got to do the 6 of them times 2 C double bonded to an O's per molecule times the 191 that it takes. That comes out to be 2292. Then let's think about the H2O molecules. Again, there's 2 OH that form per molecule, and there's 8 molecules from the balanced equation. So we got to do 8 times 2 per molecule times the energy we get for those, 1792. So add both of these together, this is how much energy we're getting back, 4,084. It's like going to the bank. This is what you're getting out. So you put 3176 in, and you're getting 4,084 back. So 3176 minus 4084, the heat of reaction is a negative 908 calories per mole. That's the heat of reaction. So it's exothermic because it's a negative heat of reaction because more energy was given off in the making of the new bonds than the energy it took to break the bonds. And then switching gears to the last couple on this page, it says calculate the molarity of these solutions. So let's take a look at our molarity triangle. Molarity is moles divided by liters. So for this first one, it's 0.4 moles divided by 1.6 liters. It's that simple. You just plug it in. So the concentration's 0.25 molar. For the second one, it's not so easy because it gives you how many grams of potassium nitrate you're dissolving in water, and it doesn't tell you liters either. It gives you milliliters, so we've got to divide by 1,000. So let's divide KNO3 by its molar mass. So I added up 1K, 1N, and 3 oxygens, and it adds to 101.11 grams per mole. So we're talking about 0.2 moles that we're putting in the 0.25 liters. That comes out to be a concentration of 0.8 molar. That's the end of page